Hi everyone, in this video we'll talk about AVL trees. Now before I start talking about AVL trees, I will quickly recall binary search trees because it is one of the issues that occurs in binary search trees, specifically balancing, which AVL trees address. So binary search trees, or BSTs. Now, if you're familiar with BSTs and you can skip this portion of the video and just move ahead, are those trees which are rooted. It's a rooted binary tree. Okay, a rooted binary tree, and so it's a binary tree. So every node can only have at most two children. Now each node has a key, a left pointer, a right pointer, and a parent pointer. Okay, so these are the things that a node in a binary search tree has. Okay, so this is just a quick recap so that we can understand AVL trees. So an example of a binary search tree is this one. So there's say 41, 20, 11, 29, and 26, and 65, and 50. So these are the nodes in a binary search tree. So what are the heights of these? So the leaf nodes have a height of 0, while 29 and 65 have a height of 1, 20 has a height of 2, while 41 has a height of 3. Okay, so these are the heights of the different nodes in the binary search tree. Now, BSTs have an important property called the binary search tree property. So what is the BST property? At any node X, all the keys in the left subtree are less than that node, or the key at that node, and all keys in the right subtree are greater than the key that node. So if X is the key at this particular node, every node in this left subtree has a key less than equal to X, and every node in the right subtree has key greater than equal to X. Now if it's greater, you can insert in any side of the binary search tree. It does not matter. Okay, now we just mentioned the height of this binary search tree, of this particular binary search tree, is 3, and by definition it is the length of the longest downward path to the loop. So here the length of the longest downward path to the leaf node is, you kind of go here, and hence it is 3. Okay, so in a binary search tree, one of the biggest issues that can occur is that the tree may not be balanced. Now it is very important for it that a tree be balanced. So importance of being balanced, and all this is needed for us to understand why we need to study AVL trees. Now, why do we want the tree to be balanced? If the tree is not balanced, what will happen is the insert, delete, all these operations in a BST will take more than O of log n. Okay, so BST operations, in general, the way you find out the runtime of the BST operations, so say insert and delete, these are the important ones. They take O of H, where H is the height of the binary search tree. Now, if it's a balanced or a perfectly balanced binary search tree, what you will have is the height to be log n, whereas if it's imbalanced, it'll actually be n. So let's look at an example. So here, this is an example of a perfectly balanced, and I am not defined what is balanced, but at this point precisely, but you can understand that in this tree, at every at each node, the number of nodes in the left subtree and the right subtree are equal. So it's a perfectly balanced tree. Okay, so it's a perfectly balanced tree, and the height of such a tree is h is O of log n. Therefore, insertion and deletion in this particular tree will occur in O of log n time. In comparison, you can also have a binary search tree which looks like a path or a linked list. In this case, the height will be O of n itself. So if you have this is an unbalanced tree. Actually, it's very badly balanced, but it is an unbalanced tree. If you have this kind of imbalance, what is going to happen is height will become n. So it's basically similar to a linked list in this case. So a binary search tree is not very useful. So you don't have the height to be log n, so it's not balanced. So all your insertions and deletions would now take O of n time. So what we want is, we want to balance the tree. Okay, we want to balance so that all operations run in O of log n. This is the reason for balancing. Okay, this is the main and primary reason why you would like to balance a binary search tree. Now there are many different trees which are balanced trees. In this video, we are going to talk about AVL trees. We're going to talk about AVL trees, and they are named after the three scientists who discovered these trees: Adelson, Welsky, and Landis. And they discovered this in 1962. So that's why this tree is called AVL tree. Now, in an AVL tree, to make sure that the tree is balanced, what we have is, for every node, AVL tree requires height of left and right children to differ at most by ±1. Okay, so what does this mean? We'll talk about this with an example, but you want the heights at every node to actually differ by at most ±1. Now, if a tree has no nodes in it, has height -1. Okay, if a tree with no nodes has height -1. Okay, now what do we have to do to implement such a tree? Each node has to store height. This is something that will augment the data structure of the node to store its height. Now, note that this kind of tree can look, for the naked eye, could look pretty imbalanced. This is because at each node, the height can differ by at most ±1. So you can get a tree which looks pretty lopsided. But as long as we maintain this criteria, we'll make sure that the tree is balanced and all operations run in O of log n. Now, I'm not going to go into the mathematical details as to why the height of the tree is log n. I'll first talk about about AVL insertions. And I'm going to talk about that with an example. So how do we go about insertion? So in this video, we'll mainly talk about insertion, and AVL deletion is going to be similar, but we'll just focus on insertion. So the first, what you'll do is, you'll insert as a BST. Okay, so the AVL tree is a binary search tree, so it'll insert as a BST. Now, when you insert a node, the AVL property can get damaged. That is, the AVL property may not hold true. So you have to work your way up, restoring the AVL property. That's what you will have to do. So you'll have to constantly make sure that the AVL property holds true. And while you restore the AVL property, you will update the heights. This is what you will try to do. Now, we will start from the bottom or the leaf, and you'll make your way all the way up to the root. Now, in each step, what you're going to do is the following. So in each step, let X be the node that violates the AVL property. Okay? Suppose X is the lowest node violating the AVL property. Okay? So now what we can assume, we are going to assume here is X is right heavy. So what do we mean that the AVL property is violated? That means that the difference between the heights is not plus minus 1. It is greater than or 1 or less than minus 1. Now, because we are moving from the bottom to the top, the imbalance can only be one more. That is, the height can now become 2 instead of, the height difference can become 2 instead of 1. Okay, so we're going to fix that and we're going to move up. Okay, so it cannot be worse than that. Now, there are two cases that we have to consider. So we are assuming that X is right heavy, and I'll just show that pictorial in a moment what I mean by that. Now, there are one case. The first case is X's right child is right heavy or balanced. Okay, so X's right child is right heavy or balanced. Now we are assuming that X is right heavy. So let's assume that this is X. Then there is Y here. Then there is A, which is the left subtree of X. And at Y, there are two subtrees, B and C. Now, what I'm going to do here is I'm going to write the heights. Now, X is right heavy. Okay, so it's the node where the AVL property is lost. So it is kind of doubly right heavy. Okay, now we assume that Y is right heavy, so or balanced. So let's just consider that Y is right heavy. So that's what I'm denoting with these arrows. So because Y is right heavy, you can assume that C, the subtree, has a height of K, while B has a height of K minus 1. Therefore, Y has a height of K plus 1. Now, X violates the AVL property and it's doubly right heavy. So the height of the subtree A has to be K minus 1, because then the difference is going to be 2. This is case it happens when the X right child, which is Y, is right heavy. X right child Y can also be balanced. So let's consider that scenario. So you have X here, you have Y, it's the same thing. X has A and Y has two subtrees, B and C. If we look at the heights, Y is balanced. Okay, so that's, and X is doubly right heavy. Okay, so because it's balanced, C and B should have the same height K, and X is doubly right heavy, so Y should have a height of K plus 1 and A should have a height of K minus 1. Now in this scenario, if this happens, okay, what are we going to do? We are going to whenever this happens, we're going to use this notion of rotation. Okay, so what I'm going to talk to you now is rotation. Rotation is the method by which we fix any kind of imbalance. So we are going to apply a left rotation on X. Similarly, the same thing also happens if Y is balanced. So we're going to apply a left rotation or left rotate X. If you do that, what is going to happen? So if you left rotate X, X is essentially going to move down here, Y is going to move up there. That is how you should think of it. You can think of it as a pulley pulling down X, and then automatically Y just moves up. So Y moves up here, becomes the parent of X. X comes down here. Now A continues to be the left subchild or subtree of X. Now Y, as Y has now become the parent of X, what is going to happen is Y cannot have three children. So B is now going to be the right subtree of X, and C is going to be the right subtree of Y. Now, if B becomes the right subtree of X, it does not matter because all nodes in B have keys greater than Y. So they're definitely going to have keys greater than X. So the BST property is not going to get violated if B becomes the right subtree of X. Now let's look at the heights. Now A has a height of k minus 1. B also has a height of k minus 1. Therefore, X is going to be balanced and is going to have a height of k. Now C in this case is also going to be balanced. C is going to have a height of k and Y is going to be balanced. So we have fixed this imbalance by this left rotation. Now we're going to apply the same logic if Y is balanced. That is, we're going to apply X, a left rotation on X. That is basically Y will move up. So here we will have Y, we have X, we have the left subtree rooted at left subtree A, the right subtree B, and we will have C. Now, if you put the heights, C has a height of k here, B has a height of k, A has a height of k minus 1. So X is now right heavy, but it's only singly right heavy, that's fine. Its height is going to be k plus 1. And you can see that Y is going to be now left heavy, but it's only going to be singly left heavy, and this is balanced. So you're going to do a left rotation on X. Okay. Now, so this is the first case. If X's right child is right heavy or balanced. The other case is else. Okay, that's case 2, which is else. Else. Okay, if X's right child is not right heavy or balanced, that is, it is left heavy. Okay, that's the else case. Now, in that case, we are going to look at it in this way. We will see that a single rotation will not be able to fix the imbalance, and we'll have to do 2 rotations. So X is going to be doubly right heavy, but its child, in this case we are going to consider the child as Z, is going to be left heavy. And this is how we are going to draw these subtrees. Okay, so A, B, C, and D. Now X is going to be doubly right heavy, Z is going to be left heavy, and we don't care about Y or A and D. Now Z has a height of k plus 1, therefore A should be k minus 1. That's why X is doubly right heavy. Now Z is left heavy, so Y has a height of k, and D has a height of k minus 1. Okay. Now A, B, and C can have height of k minus 1 or k minus 2. Okay. Now what you're going to do is you are going to first apply 2 rotations here. We'll see that 1 rotation will not be sufficient. Now here the thing to notice is we have a zigzag kind of scenario. If you have a zigzag kind of scenario, you'll have to do 2 rotations. So first we are going to right rotate z. If you right rotate z, z is going to come down like this, y is going to move up like that. Okay, so you'll have x, z and y in a straight line. It'll look something like this. So x, y and z, you'll have them in a straight line. Okay, and we'll understand this better when we look at a concrete example. After you right rotate z, you will left rotate x, because after you get this scenario, it is very similar to the previous scenarios that we looked at. So you will, to get this, you will left rotate x. So x will go like up like this, y will go up like this and will become x's parent. So after you do 2 rotations, you will have the image or the tree look like this. There is y, there is x, there is z, and x will have 2 subtrees A and B, z will have a subtree C and D. And if you look at the heights, you will see that A has a height of k minus 1, okay. B and C have a height of k minus 1 or k minus 2, and D also has a height of k minus 1. Okay, therefore X and Z will have heights of k, and they will be either balanced. X could be either balanced like this, or it could be heavy in this direction, or other way around. Actually, X could be balanced, or it will be heavy in this direction. Z could be balanced, or it could be heavy in this direction. Okay, does not matter. And Y is balanced, and it has a height of k plus 1. So these are the 2 cases. Okay, so either these 2 scenarios occurs if X's right child is right heavy or balanced, or if X's right child is left heavy. Okay. Now, similar set of 2 cases will occur if we consider X is left heavy. So here we have considered that X is right heavy. Now, 2 other options like this will occur if X is light heavy. Now, once you fix this, you'll have to move up the tree fixing violations. Okay, so either you have to use a single rotation, or you have to use a double rotation or 2 rotations. Okay, so now now that we have looked at this case, let us look at the other case where X is left heavy, or going to be doubly left heavy, and look at the 2 other cases. And we'll do that with a concrete example. So let's consider that this is your binary search tree. You have 41, 20, 11, 29, and 26. And on the right side, you have 65 and 50. Okay, so this is your binary search tree. Let's just go and put in the heights. The leaves have heights of 0. 65 has a height of 1, and it is heavy in this direction. 29 has a height of 1, it's heavy in this direction. 20 has a height of 2, it's heavy in the right direction. And 41 is heavy in the left direction as a height of 3. Now let's insert 23. So let's just insert 23. Now when you insert this new node, it is going to get inserted on the left side of 26. So let's just draw this. So it'll be 41, 20, 11, 29, 26, and then you will insert 23 here. And you'll have 65 and 50. So if you go about putting the heights here are, this is going to be 0, this is 0, this is 1, and it's going to be left heavy, and you will see that this has a height of 2 and 29 is right heavy. And you can just put the heights here. So now there is a violation at 29. Okay, so violation at 29, that is 29 is doubly left heavy. Okay, and what we have is 29 is doubly left heavy and its child 26 is left heavy. So what we have is basically the left case. Basically all these three are in a straight line. So a single rotation should actually fix it. So let's just try to do that. So for that I'm just going to copy this over again. So we have 41, 20, 11, 29, 26, and 23. I'm so sorry, this is incorrect. Erase this. We have 29, 26, and 23, 65, and 50. Now, just by putting back the heights, this is going to be 2, 1, 0. This is balanced. This is the left. This is doubly left. And this is okay. So now what we are going to do is we are going to rotate. Okay, if you rotate by pulling 29 in this direction and 26 up, what is going to happen is this. So we can right rotate 29. That's what we will do. Okay, so if you right rotate 29, right rotate 29, 29 will come down, 26 will become its parent. So we'll have 41, 20, 11, 26 here, 29, and 23. If you put the heights, this is going to be 0, 0, just use red color with for heights. This is a 0, this is 0, this is also 0. 26 has a height of 1 and it's balanced. 20 will have a height of 2 and it's balanced. It's not balanced, it's just singly right heavy. Now look at the other nodes here, 65 and 50. Nothing has changed in those nodes. Their heights are anyway going to remain exactly the same. It's going to be, and just fixing this single rotation fixes the tree. So once this violation is fixed, there are no other violations higher up in the tree. So this is the left case. Now let us insert 55 into this tree. So to insert 55, so we're going to insert 55, which is basically going to come to the right hand side of 50. So let's just do that. So here what we're going to do is insert 55. So we're inserting 55. I'm going to draw the tree here. Now, inserting 55 will result in the tree to look like this. So you will have 41, 20, 11. Everything on the left subtree of 41 will remain exactly the same. There is no major change here. 55 will get inserted on the right side of 50. So this is where 55 will get inserted. Now let's just put the heights. You will see that this is 0, this is 0, this is 1, and it's 26 is balanced. 11 has a height of 0, 20 has a height of 2, it's right heavy. Now if you look at 55, that has a height of 0, 50 has a height of 1, and it's right heavy. 65 has a height of 2, and it's doubly right heavy because it has no child. Okay, so at this stage we will have to fix it, and we will have to apply 2 rotations. So what we have is, we have if the other one was a zigzag, this is the zag-zig case. Okay, so go up. See, we had the zigzag here. It's just the other side, the zag-zig. So we will have to do 2 rotations. Okay, this is essentially the left-right case. Okay, so first what we will have to do is we will have to first make them come in a straight line. So we will first do 1 rotation to get them in a straight line. So what is that we will have to do? To do that, we will essentially left rotate 50. So if you left rotate 50, what will happen is you will have 65. I'm just going to concentrate on those 3 nodes. 65, 55, and 50 will form this straight line. And then if we right rotate 55, if we right rotate 55, after that, what we will get is, we will have 65 coming down, and finally what will happen is you will have 55, 50, and 65 in here. So we have to right rotate actually 65. So bring 65 down, 55 will move up. Right rotate 65 down. Raise that. Okay, that's what we did. Now let us see how the tree will look like after we have done this. Okay, so the final tree, I'm just going to erase these 2 things here. Erase all this. So the tree will look like this. So I'll have 41, 20, 11, 26, 23, and 29. And you will have 55, 50, and 65. Okay, so you will left rotated 50 to get 50, 65, 55, and 50 in a straight line. Then we right rotated 65 to actually get 55 to have 2 children, 50 to the left and 65 to the right. Now if we put the heights, this is going to be 0, this is balanced with a height of 1, this is balanced with a height of 0, this will have a height of 2, 1 imbalance on the right, but that's fine. These 2 will have heights of 0, and this one will have a height of 1, and 41 will have a height of 3, and we left heavy. But with this, we've actually fixed all the violations, and there are no other violations to fix. Now, with this, by doing this, an AVL tree has height O of log n. Hence, all operations will execute in O of log n. So this is why AVL trees are so important. So in this video, I mainly talked about AVL tree insertion. Deletion is similar to this, but in this video, I will only talk about AVL trees from the perspective of insertion. And I hope that you understood from this video why balancing is important and how you balance an AVL tree. Thank you for watching.